Hello. In this video, I will show you some examples on how you can use Interface Equilibrator to study colloidal particles at flat fluid interfaces. Let's consider, for example, a colloidal particle with a cylindrical shape. So, we can load it from the built-in meshes. For example, let's use a cylinder with height 6 micron and radius 1 micron. We have now loaded the mesh for the solid particle. Let's now load also the mesh for the fluid interface. We select the circular meniscus, and we set an opportune radius that is large enough with respect to the particle size. We now need to create a hole in the meniscus center so that we can then use the particle as constraint for the boundary of the hole. However, before creating the hole in the fluid interface mesh, we save its current surface area for later convenience. We can get it by clicking Mesh Surface Area. This is the area of the current fluid interface mesh. That is, the area of the fluid interface when no particle is adsorbed at it. We also get the surface area of the cylinder mesh. So, we click Mesh Surface Area after right-clicking the particles node in the tree diagram. This is the total surface area of the cylinder's mesh. Let's now create the hole in the fluid interface mesh. We right-click the fluid interface mesh in the tree diagram, and then we click Remove Facets. Then, we can easily select the facets to be removed using the mouse cursor, and then we click Confirm. We have now created a fluid interface mesh with the correct topology. Let's edit the names of its two boundaries to remember which one is which. Let's also set the Young's contact angle of the particle. We right-click the cylinder node in the tree diagram, and we click Edit Theta. Let's set, for example, a contact angle of 60 degrees. The contact angle value is always taken in the fluid below the fluid interface. To check which one is the fluid below, you can show the interface normals, which always point toward the fluid above. Let's select the constraint for the interface's external boundary. We select Display only in Z. In this way, the vertexes of this boundary are allowed to move only vertically. As contact angle for this boundary, we leave 90 degrees. So, far away from the particle, the fluid interface will behave as a flat interface. Let's also select the settings for the equilibration. We want to run a first equilibration keeping the fluid interface mesh not too much refined, to find an initial shape close enough to its equilibrium shape. And then later we will run a second equilibration where we refine more the mesh. Let's save the current configuration for later convenience. Let's now set the cylindrical particle as constraint for the fluid interface inner boundary to calculate the interface's equilibrium shape when the cylinder is adsorbed at the interface in this orientation. As you can see, at the equilibrium, the interface forms a capillary monopolar deformation near the cylinder, induced by the cylinder's contact angle. Let's now run another equilibration, allowing a finer refinement for the mesh, using this as initial mesh for the fluid interface, to find a more accurate equilibrium shape. Notice that the position of the solid particle is fixed in Interface Equilibrator. For this reason, we obtain this capillary monopolar deformation near the cylinder. However, if the particle was free to move vertically, like in reality, then it would sink in the fluid below, minimizing the capillary deformations in the interface. In Interface Equilibrator, we can mimic this behavior by allowing volume exchange between the fluids during the equilibration. Indeed, if the equilibrium shape of the fluid interface is computed without keeping the fluid volumes fixed, then the volumes of the fluids will automatically adjust themselves so that the fluid interface reaches its equilibrium height with respect to the solid particle. Let's first reload the initial configuration we saved before. Then, we open the equilibration settings and we select the Advanced tab. In this tab, we select the option, Allow volume exchange between the fluids. Notice that, when this option is activated, the fluid-fluid pressure difference is 0. Therefore, the fluid interface will be stable only if its bed curvature is flat, which is the case here. Because we allow volume exchange between the fluids, the initial shape of the fluid interface might be far from the equilibrium shape. So, it's important to run a first equilibration keeping a lowly refined mesh to ensure that the fluid interface reaches its equilibrium shape. Let's set again the cylinder as constraint for the inner boundary of the fluid interface. And then we launch again the equilibration. This time, the fluid volume is allowed to vary, while the fluid interface equilibrium shape is computed. And, as expected, the interface level has risen so that the whole particle is wet. We still see a residual, small monopolar capillary deformation near the cylinder. This is likely due to the poor refinement of the mesh. So, let's launch a new equilibration, allowing a finer refinement of the mesh. With this more refined mesh, the obtained equilibrium shape of the fluid interface is essentially flat. There is still a very small deformation near the cylinder, but this is very small compared to the scale of the system. As we can see by zooming out a bit, the scale of the height contour plot. If you were to run a new equilibration with an even more refined mesh, the obtained equilibrium shape would likely be even more flat. This result tells us how the cylindrical particle would stay adsorbed at a flat fluid interface if the particle was fixed in its vertical orientation. However, in real systems, the particle would also be able to rotate. So, how can we predict which is the equilibrium orientation of the particle at the fluid interface? The answer is, by finding which orientation of the particle minimizes the energy. For particles at fluid interfaces, the energy can be written with this expression, where S is the surface area of the fluid interface, W is the surface area of the particle wet by the fluid below, gamma is the fluid-fluid surface tension, theta is Young's contact angle, taken in the fluid below. In our case, 60 degrees. So, we need to calculate the energy E for different particles' orientations to find which orientation has the lowest E. Let's start from a cylinder in the vertical orientation, for which we already computed the fluid interface equilibrium shape. To get the fluid interface area, we click Mesh Surface Area, after right-clicking the fluid interface node. This is the area of the fluid interface equilibrium shape, with the cylinder adsorbed in the vertical orientation. Then, we need the surface area of the cylinder that is wet by the fluid below. Interface Equilibrator can calculate this quantity. We right-click the node of the boundary that is constrained on the particle surface, and then we click Solid Surface Area Wet by Fluid below. This area is computed using the shape of the boundary that is constrained on the solid surface mesh. While this tool is open, this surface area is highlighted in red so that we can see which is the solid surface wet by the fluid below. Let's hide, for a moment, the solid surface mesh so that we can see better the solid surface area wet by the fluid below. So, now that we have also this value, we can write down the energy E for the cylinder adsorbed at the fluid interface in the vertical orientation by using the values for S and W that we just retrieved. Then, we can find the adsorption energy of the cylinder at the fluid interface as the energy E minus E0, where E0 is the energy of the cylinder when fully immersed in the fluid below. And we can compute E0 using the values for S0 and W0 that we retrieved before, where S0 is the area of the flat fluid interface without the hole, and W0 is the total surface of the cylinder. We can repeat this procedure to compute the adsorption energy of the cylinder in a different orientation at the interface. So, we first reloaded the previous configuration. Then, we rotate the cylinder, for example, by 45 degrees. Then, we set this tilted cylinder as constraint for the fluid interface in a boundary. We activate the option to allow volume exchange between the fluids, so the fluid interface can find its equilibrium height with respect to the particle. The remaining equilibration settings were already saved in the configuration we loaded. We then launch the equilibration. So, the fluid interface finds its equilibrium height and shape with respect to the particle. Then, as usual, we launch a second equilibration, allowing a finer refinement of the fluid interface mesh. We have now obtained the equilibrium shape of the fluid interface for the tilted cylinder, and we can now compute its adsorption energy. First, let's get the surface area of the fluid interface shape. Then, let's get the surface area of the particle that is wet by the fluid below, by right-clicking the node of the boundary constrained on the particle, and then by clicking Get Surface Area Wet by the fluid below, which we can now see highlighted in red. By writing down these values, we can then calculate the energy for the cylinder adsorbed in this tilted orientation at the fluid interface. As you can see, the energy of the cylinder in the tilted configuration at the fluid interface is higher than the energy of the cylinder in the vertical configuration at the interface. This means that the cylinder prefers staying vertically at the interface rather than tilted. Let's now consider an horizontal cylinder at the interface. So, we reloaded the previous configuration, and then we rotate the cylinder by 90 degrees, so that it stays horizontally at the interface. Then, we set the cylinder as constraint for the fluid interface in a boundary. Finally, we enable volume exchange between the fluids, and we keep these equilibration settings that we set before. We launch the equilibration, and the equilibrium height and shape of the fluid interface is obtained. We now launch another equilibration, allowing a finer refinement of the mesh. Interestingly, we have found that, when adsorbed horizontally, the cylinder creates a quadruple capillary deformation field. Let's get the area of the fluid interface for the cylinder in this orientation. and then the area of the particle that is wet by the fluid below, which is now highlighted in red. From these quantities, we can now obtain the energy of adsorption for the cylinder in the horizontal orientation at the interface. By plotting the adsorption energy of the cylinder with respect to the cylinder's orientation, we see that the horizontal orientation has the lowest energy. Therefore, the cylinder prefers staying horizontally at the interface. In addition, the vertical orientation seems metastable. So, the cylinder might be found also in the vertical orientation. By calculating the adsorption energy of the cylinder also in other orientations, you can obtain a finer plot of the energy landscape with respect to the cylinder orientation at the interface. With a similar approach, we can also measure the capillary interactions between multiple particles at a fluid interface. Let's reload the same cylindrical particle we used in our previous example, to use the same shape also in the next example. As before, we select 60 degrees as Young's contact angle for this particle. Then, we rotate the particle in the horizontal orientation, which, as we found before, is its equilibrium orientation at the fluid interface. For later convenience, we save this mesh on an external file. We now want to load a second solid particle, identical to the one we already loaded. So, we'll load it from the file we just saved. We have now loaded a second particle, identical to the first one. Let's translate the two particles opportunely so that they are near each other, with their bases in front of each other. So, we translate the first particle in the negative x direction. And then we translate the second particle in the positive x direction. Now the two particles are at a surface-to-surface distance of 1 micron. Let's load also the mesh for the fluid interface. This time, we select the rectangular meniscus, setting its size opportunely so that its borders are far away from the particles. Then, we'll launch the tool to remove facets, to create a hole in the center of this meniscus. However, this is not yet the correct topology for the fluid interface mesh, because we need to have two holes, one per particle. So, we need to connect these two boundaries of the hole that we just created. For doing this, first, for convenience, we refine a bit the mesh facets where we want to make the connection. Then, we add a second rectangular meniscus, with an opportune size to fit in between the two particles. We have loaded this smaller meniscus. Now we want to connect its boundaries to the boundary of the external hole, to create a single fluid interface mesh. First, we right-click the node of the new mesh, and we select Add Capillary Bridge by connecting boundaries. With this tool, first, we select a boundary vertex of the new mesh. Then, we confirm it, and we select a boundary vertex of the other mesh in the point where we want to make the connection. And once we click Confirm, the connection is made. Now we have a single mesh for the fluid interface. and we only need to connect these boundaries to complete the desired topology. For doing this, we select the Add Facets tool of the mesh, and then we click by connecting boundaries. This tool works like the previous one. That is, we select the two boundary vertexes where we want to make the connection. And then we click Confirm. We have now created a fluid interface mesh with the desired topology. Let's edit the names of its boundaries to remember which one is which. This is the boundary one. I momentarily hide the first cylinder. So, the first cylinder is that inside the boundary one. Let's select the constraint for the fluid interface external boundary. Like before, we select Displace only in Z, and we leave a contact angle of 90 degrees to mimic a flat fluid interface far away from the particles. Then, we enable the option to allow fluid volume exchange during the equilibration, to allow the fluid interface to find its equilibrium height with respect to the particles. Finally, we set a low refinement for the mesh, to ensure the mesh finds its equilibrium height. Then later we'll launch another equilibration allowing a finer refinement. Let's save the current configuration for later convenience. We now select the cylinder 1 as constraint for the first boundary. As you see, we got this error message saying that the constraint cannot be set. This error occurs after selecting a solid surface as constraint, and after the boundary vertexes are displaced on the solid surface. If some edges of the fluid interface mesh, going from a boundary vertex to an inner vertex, are placed on different sides of the solid surface mesh. In this case, it would seem that all such edges are on the same side of the solid surface mesh. However, if I make the cylinder mesh semi-transparent, we see that these two edges, going from an inner vertex to a boundary vertex, actually originate from the inner side of the solid surface. So, when this problem occurs, the constraint cannot be set. The solution is to edit the fluid interface mesh opportunely, so that when setting the constraint, this problem does not arise. For convenience, let's reload the configuration we saved before. For example, in this case, to avoid this problem, we can lower a bit in between the two particles, the vertexes of the fluid interface mesh. In this way, when we will select the constraint, all edges going from an inner vertex to a boundary vertex should end up staying on the external side of the solid particle. As you see, we have edited the shape of the fluid interface mesh, lowering a bit its vertexes in between the two particles. Let's now select again cylinder 1 as constraint for the first boundary. This time, the constraint is successfully selected. Then, we select cylinder 2 as constraint for the second boundary, and also this constraint is successfully selected. We can now launch the equilibration, and the fluid interface mesh finds its equilibrium height with respect to the two particles. We now want to launch another equilibration to further refine the mesh. To be able to measure capillary interactions, we need a highly refined mesh. So we are going to refine the mesh in steps. That is, we now launch a second equilibration with a mediumly refined mesh. And then later we will launch a third equilibration, where we will refine the mesh even more. So, let's now set a very high refinement for the mesh. And then we can launch the equilibration again. In addition, when setting a very high refinement for the mesh, it is recommended to disable this option, which is used to keep the fluid volume exactly constant when polishing the mesh, as this might create problems when the mesh has very small facets. Besides, we don't need this option, since we are allowing volume exchange between the fluids. So, we launch a new equilibration, this time having selected a very high refinement for the mesh. It seems we have obtained a good equilibrium shape. The symmetry of this equilibrium shape is a good indicator that we reached an adequate approximation. However, because we need an extremely good approximation to precisely measure capillary interactions, we will now launch a final equilibration to further optimize the equilibrium shape. We select the manual setup, where we can set manually for how long the equilibration is ran. We select 10 million Monte Carlo steps per vertex. In addition, when using the manual setup, the fluid interface mesh triangulation is not edited. The diagnostic panel at the bottom of the window, which is now plotting the energy variation during the equilibration, shows that we are doing some minor optimization on the equilibrium shape at the level of the fourth relevant digit. We have now obtained an equilibrium shape with a reasonably good approximation. Let's get the surface area of the fluid interface. And then the surface area wet by the fluid below of the first cylinder, now highlighted in red. And the surface area wet by the fluid below of the second cylinder. By writing down these values, we can calculate the energy E for this system of two particles at the fluid interface. In addition, we can then write the particle-particle interaction energy, using this expression here, where E0 is the energy of the system when the two particles are fully immersed in the fluid below, where S0 is the surface area of the flat fluid interface without holes, and E1 is the energy of adsorption of a single cylinder in the horizontal configuration, which we calculated before. Let's now repeat the calculation we just did, but placing the two cylindrical particles closer together. So we translate the first cylinder in the positive x direction, and the second cylinder in the negative x direction. So, the two cylinders are now at a distance of 0.1 micron. Let's also edit the shape of the fluid interface mesh by lowering a bit its vertexes in between the two particles, so that later we can select successfully the two cylinders as constraints for the boundaries of the fluid interface. Finally, let's select the two cylinders as constraints for the two boundaries. Cylinder 1 for the first boundary, and for the second boundary, cylinder 2. We can now launch the equilibration. As usual, we initially keep the mesh refinement low to ensure that the fluid interface finds its equilibrium height with respect to the particles. We can now launch another equilibration, setting a medium refinement level for the mesh. Finally, like before, we will run a third equilibration, where we set a very high refinement level for the mesh, because we need a highly refined mesh to measure capillary interactions. In addition, like before, we disable this option, since it might create problems for highly refined meshes. Let's start the equilibration. We hide the two cylinders so that we can more easily check the obtained shape for the fluid interface. The narrow capillary bridge in between the two particles appears to have been calculated correctly. However, it does seem that there was a problem with the boundary near the left base on the cylinder on the left. This kind of problems can occur sometimes when the mesh is highly refined, because the mesh shape remains stuck during the equilibration due to clusters of very small facets. The best solution to fix these problems, if they arise, usually is to simply relaunch the equilibration using the same settings, so that the methods to refine and polish the fluid interface mesh should eventually clear the problem. The equilibrium shape has now been computed. And this time it does seem that the calculation was done correctly, since the boundaries of the fluid interface appear quite smooth everywhere. The shape of the narrow capillary bridge in between the two particles also appears to have been calculated correctly. Like before, we will now launch a final equilibration using the manual setup to further optimize the equilibrium shape of the fluid interface. Since, to precisely measure capillary interactions, we need to obtain a very good approximation in the equilibrium shape of the fluid interface. The calculation of the equilibrium shape was completed, and the symmetry of the solution is a good indicator that we obtained a satisfactory approximation. Let's now get the surface area of the fluid interface. And the solid surface area wet by the fluid below of the first cylinder. And of the second cylinder. We can now write down these values. And like we did before, we use them to compute the particle-particle interaction energy, which now appears lower than before, as expected, because the particles are closer to each other. By plotting these values with respect to the particle-particle distance, we can see how the capillary interaction between the two particles varies. And by repeating the calculation for different distances, you can obtain a finer plot for this potential. In addition, because these energies are quite sensible to the numerical approximations in the fluid interface equilibrium shape, you can also repeat the calculation several times for each distance, and then take the average energy for each distance to obtain more precise values. Finally, you can repeat these calculations for different reciprocal orientations of the particles to investigate how this affects their capillary interactions. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.